All right. Let's go ahead and pick up where we left off. Like I said last time, we have a couple examples left to look at. All right, so continuing optimization. Let's take a look at this situation. A picture drawn. A man launches a boat from point A, wants to reach B as quickly as possible. He can row at 6 kilometers per hour and run at 8 kilometers per hour. So basically, he's deciding where that point D is. And we're assuming this river is still enough that it's not affecting the speed that he's rowing. So we have a picture. We're trying to optimize what? Like we're trying to find a minimum or a maximum of what thing? Actually not trying to minimize distance necessarily. Trying to minimize time, right? So we want to minimize time. All right, so that's a good thing to realize. What else do we need to do here? What are the variables at play? We have an angle, yes. I'm going to steer us away from that. Yeah, we could do this in terms, we could take like a trigonometric approach to this. I'm going to steer us away from that. Yeah, so the river is going to be a constant 3 meters or 3 kilometers in width. Okay. So we know this distance from A to C is 3 kilometers. We know from A to, actually we don't know A to B. We know from C to B is 8 kilometers. Where should we start assigning variables here? Like we're gonna basically like, you know, the metaphorical knob here that we're gonna try to dial in. What should that variable be? If I were to trace his path, so he's starting from A to B, right? Not directly, maybe directly, but not necessarily. How would I trace that path from A to B? Like what's the way he's actually going to go? So he's going to go A to D first, right? So basically what we're trying to do is this. I want to find out where that D is that makes this time the least. He's going to row from A to D, and he's going to run from D to B. So I think that's what we want to think about. Variables. So what's the variable we actually have control over? Let's say this. Let's call this variable right here X. That's like if we have control over that, we have control over everything, right? So we want to minimize time. How much time is this going to take him? So let's break this up into 2 pieces. The time it takes him to get from A to D, and the time it takes him to get from D to B. How can we express how long it's going to take him to get from A to D? So that's the rate, right? So the 6 kilometers per hour is going to be his speed as he goes from A to D, right? But we're trying to minimize not speed. Speed is constant as far as we're concerned. We're trying to minimize time. So we know that he rows at that speed, 6 kilometers per hour. How can I translate that to a time between A and D? Right. Sebastian, what do you got? Is it really 3 kilometers though? I think the only way that 3 kilometers is the distance he rows is if he rows straight across, right? So really what we're going to look at is this distance right here from A to D. So how can I find that distance from A to D? Is it, well, sorry, I heard a lot of things going on there. You could use trig. I'm going to try to keep us away from that. Yeah, your Pythagorean theorem, I heard, yeah, from tongue and tall. So yeah, we want to get Pythagorean theorem involved here. So what specifically is that expression going to look like? Square root of 9 plus x squared. Why 9? Right, so yeah. X squared plus 3 squared is equal to the distance squared. Kind of simplifying it all in one shot there. So that's the distance, right? While we're at it, let's do this. What's the distance from B to D? I guess I called it dB. What's that distance? That one should be a little other way, yep. So yeah, so in dialing in this distance x, I mean that's the variable we want to control over. We know this distance is just whatever is left after we subtract x from b. So now that I have those 2 pieces of information, what can I do? Like, can I rewrite this in a schematic, this template for an equation now? Sebastian? ABC? Yes, you could, but what would that give you? By the hypotenuse, do you mean the from A to B? Yeah. That's actually not the way he's going to go. It might be. We might find out that B is the right place to just go directly to, but we don't know that. So remember, we're trying to minimize time here. We have a good idea of how distance relates to the variable that I chose for us. How do we relate those 2 things, time and distance? Divide distance by velocity? Let's think about it this way. What is velocity a measurement of? Yeah, velocity is equal to, actually, I'm going to change this to speed. Really, that's, so speed is equal to distance over time. And since our distance is going to be fixed, like dependent on that variable x, speed is constant. Does it make sense then that we can say this? Time is equal to distance divided by speed. By manipulating that, speed equals distance over time. If that's true, then how can we rewrite this equation? So time is a function of x. Yep. So we should pause there to make sure everyone's okay with where that equation came from. This one's quite a bit more involved than the ones we've done in the past. Any questions about anything we've done up to this point? Where does the 6 come from? He rows at 6 kilometers per hour and he runs at 8 kilometers per hour. So yeah, I mean, that all relates back to this idea here. Time is equal to that quotient, distance divided by speed, which is probably unusual to think about time in that context. Usually you go some other direction, but that's really what we're looking at here. So now we have an equation. What should we do with it? Yeah, differentiate, yeah. Yeah, I was wondering if anybody would see that. We can definitely do that. If we split that up, it becomes 1 minus 1/8 x, which I think, yeah, that derivative will now be easier to think about. So now we take t prime of x. We get what? Someone help me with that derivative. I'll do the last two for you. How does that square root derivative shake out? Where's that 2x come from?
Well,
Yeah. I see what you're doing. Yeah, let's go a little slower here. But I think you're right. So let's start with this. I know it's gonna be 1/6 times something because that is a constant multiple there. Then I'm gonna have 1/2 times 9 plus x squared to the negative 1/2 times 2x minus 1/8. So what simplifies here? All right, I think that's good. Are we happy with that? All right, now I have a derivative. It's simplified somewhat. What should I do with that? Yeah, stereo. So how do I find critical points? Set it equal to 0. So that gives me this thing. X over 6 times the radical 9 plus x squared equals 1/8. Cross multiplying gives me this. 8x equals 9 times the square root of 9 plus x squared. How do I solve this thing? What's that? Divide by 8 will give me x equals 3/4 times radical 9 plus x. That radical is really messing us up. Yeah. Sebastian? Yeah, I'll do that now. So, did you say square or square root both sides? I'm going to go with what I think you meant. So this becomes x squared equals 9/16 times 9 plus x squared. I am out of room. So it's going to look really weird, but I am going to finish this up in the top of the margin. It becomes x squared equals 81/16 plus 9/16 times x squared. Would it be okay if I multiplied the whole thing by 16? All right. And this becomes 7x squared equals 81, and x equals the square root of 81 over 7, which is 9 divided by the square root of 7. Because I am totally out of room, I'm not going to write anything else down, but what really should we do to finish this thing off? Make sure that's a minimum. So how would we make sure that's a minimum? Number line thing. One thing you really could do here is this. I mean, you could figure out, all right, just if you rose straight to C, you could find that time. If you, or yeah, you could find that time. If you rose straight to D, you could find that time. And then you will probably find that 9 over radical 7 is less than both. I'm promising you that's the case. Yeah, this is actually a minimum. Sebastian. No, so necessarily, if I wanted to minimize my distance, what would that be? How would I find that? Or describe what that situation would look like? A to B. So A to B is the shortest distance, but it's not the fastest. Jordan, do you have a question?
Yeah.
Yeah, so one of the only values makes sense for this question particularly. Anything else on this one? All right, last one. I want to find the largest rectangle that can be inscribed in a semicircle of radius 10. All right. What should I do first?
Right.
What's that? Largest by area. Yep. All right, I'm gonna let you on. What should I do? I could. Let's do that. So, semicircle. I'm gonna put a rectangle in it. All right, so, and I want to find its area, right? We all know how to find the area of a rectangle, I hope. Yeah, so I'll call this width, call this length. So I think we got an idea of the thing I'm trying to optimize, which is area is equal to length times width. So let's optimize this thing. But we don't have free reign over that really. What's our constraint going to look like? That's the area. So I mean, what you just gave me, Cameron, would be the area of a semicircle. And really, it's not the area of the semicircle specifically that's going to like close us in. It's really just the borders of it. So yes, and let me throw this this detail on this. Let's model this circle and rectangle as taking place on a coordinate plane. So because of that, I'm gonna swap out x and y for, so we'll swap out length and width for the idea of x and y. So because of that, how do I have to modify my area for the rectangle equation? And when I say x and y, I'm saying, you know, as points on a curve or as points on a coordinate plane. Was the area just xy? No, it's a little different. Because really, what is the length of this rectangle? Like, assuming this thing is symmetrical, what are the coordinates at that point? Negative xy. So yes, I think my height is still y, or width, whatever we called it. But what is the true length of that rectangle if I'm going from negative x It's going to be 2x. So the thing I'm trying to optimize is really area is equal to 2xy. So I'm trying to draw this rectangle in a semicircle that has a radius. So it stretches between -10 and 10 on the x-axis, goes from 0 to 10 on the y-axis. Is there anything mathematically we can say about that semicircle? Centered at the origin, radius of 10. What? Okay, so we okay with that idea? So, yeah, no matter where I put the point xy, that what makes a circle a circle. That distance between the center and the circumference is 10. So because of that, I think I can also say x squared plus y squared equals what? So close. And I'll tell you right now, this is not how I was expecting this conversation to go. I was expecting to talk about, does anyone remember how you find the equation of a circle? It's x squared plus y squared equals the radius squared. Which, this is, and the way it's all described is that's why that's the equation. I mean, specifically, if you're having it centered on the origin, it's x squared plus y squared equals radius squared. So this is our constraint equation. So we have the thing we want to optimize. We have this other equation that limits what our area can be. What should we do now that we have both? I'll let you all choose what variable do you want to solve for. Sounds good. Could we have done x? I think it would work out just as well. So y squared, so I got y equals plus or minus 100 minus x squared. So I need plus or minus though? Yep, just look at the top side. So from there, I think I can do this. Area as a function of x only is equal to 2x times radical 100 minus x squared. So in my opinion, the most important part of any of these problems is to come up with this equation here. So I'll go ahead and pause and make sure that we're all happy with where this came from. Are we okay with this equation or any of the steps we took to build it? Oh, I'm sure there is. Yeah.
So you could do it with ID plus the radius.
Yeah, I'm confident there are other ways to do this. I think this is the most efficient, but by no means am I saying it's the only one. Jordan?
I just want to. The area of the one side, rectangle, and multiplying it by 2.
Yeah, because basically, so this distance right here from y-axis to right edge of the rectangle, that in itself is x. So I mean, we're still saying that area is equal to base times height, but in this case, we're saying that base is equal to 2x, and height is equal to y. So that's all an artifact of us using this Cartesian formula. All right, what should we do to keep going? Find the critical points, which means we have to find this derivative, and I need help with that one. What is this derivative? More importantly, what do we have to invoke to find this derivative?
Rule.
Product rule and chain rule. So Knowing we need those, how's this going to go? All right, so the derivative of 2x times square root of 100 minus x squared plus 2x times what? So I'll put all the building blocks in here. So chain rule says 1/2 times 100 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. And I really would like this thing to be equal to 0. So this one is about as simplified as it's going to be. That will annihilate that. So then I get minus 2x squared over the square root of 100 minus x squared. All right, any complaints or questions about this? All right, where should we go from here to solve it? Cancel in what way? If I multiply, yeah, so that's what I was, when I hear cancel, I mean, my brain goes to, it goes away. Which I don't think it totally goes away, but how does it simplify? And it becomes, all right, very good. So from here, we've got 200 minus 2x squared equals 2x squared. Then from there, you get 4x squared equals 200. So x squared equals 50, or x equals the square root of 50. So if x is equal to the square root of 50, what's the area of the largest rectangle that I can fit inside this semicircle? If x is radical 50, what's y equal to? Also square root of 50, right? So that means my area is equal to 2 times square root of 50 times square root of 50, which is 100. Let me know if you have any questions. I just kind of skipped a few steps because I'm out of real estate. X is radical 50, right? If I know X is radical 50, So I can't go straight to that. Any questions on that one? We did, and I didn't mean to, but yeah, we should definitely do that. So yeah, we need to make sure that that is the maximum. So Cameron suggested the second derivative, so let's go ahead and do that. So area double prime is equal to. What's that? So here's one thing I'm going to point us to. Here is what the first derivative is, right? Yes, we could take the second derivatives of that. But is there something else we could do that might be less intense? And this is one thing I'm not sure if I've mentioned this before, but second derivative test is really nice, but only when it's like pretty available. I think that derivative right there, it's absolutely doable by everybody in here. But I think there's something that might get us there to where we want to go quicker. Yeah, so we can find out the same information by looking at the derivative, the first derivative, at some test points. So we found that our critical value of x is radical 50, not f prime, f prime. So what are some good test values of x that we can try on either side of that? I mean, always choose one if you can, right? I'm actually going to take the extremes. I'm going to go x equals 0 and x equals 10. All right, yeah, x equals 10 makes sense. So what is a prime of 0? Should be 20, right? And what is a prime of 10? That doesn't work, does it? So we're not allowed to use 10. Let's use 8. Sounds good. All right. If we plug in 8, we should get 2 times, that's 16 minus something that's hopefully bigger than 16. Yep. 12 minus 128 over 12? Over 6. Yeah. So I'm just going to say this. So that tells us everything we want to know. Derivative increases to I actually think you could. I mean, it's kind of trivial, but you could make a rectangle that has no area at all. And you could choose to build it. Actually, no, you can't do 0 because it needs to have some kind of width, but so that I changed my mind. You cannot have a minimum rectangle. You can just keep making smaller and smaller ones. As long as you say that it has to have some width. You can make them like infinitely narrow, vertically or horizontally. Any questions here? That's a good question. All right, that is all I have for you with section 4.5. Let's move on to 4.7 briefly. Not going to finish by any means, but we can go on to it. So section 7, skipping 6, but section 7 is all about antiderivatives. So we've spent a big chunk of this semester talking about derivatives, the process of differentiation, and things you can do with that process. How we go the opposite direction. Talking about antiderivatives. So let's just warm up here. I don't want the derivatives to these 3 things. I don't want discrete derivatives. So function whose derivative. I'm going to vote for 4x. What? What's that for?
It could be any number. You could have 4x plus 3, and that would.
Right. So, and that's I didn't think we'd get there that quick, but that's a valuable idea when you're taking antiderivative. Think about what happens when you take derivatives. What happens to constants? They go to 0. So when you're going the opposite direction, taking the antiderivative of 4, how many possible functions could you have whose derivatives are 4? There's an infinite amount, right? And typically what we do here is to reflect that possibility, we just say 4x plus c, some arbitrary constant that I don't know what it is unless you give me enough information to tell you what it is. All right. How about 10x? What's a function whose derivative is 10x? 5x squared plus c. We okay with that? How are you getting that? Power rule? Taking the power rule the opposite direction? All right, how about x squared? X cubed over 3. Cool. Now you don't really, the way I asked this, so you don't need that plus c, right? I'm just asking if you could, can you give me an example? But yeah, so we're going to talk about that. So for all three of these, so that's essentially in the name antiderivative. It's not an accident. You are absolutely just, I am giving you the derivative. You tell me the function that would have yielded that derivative. So any questions on kind of what this new object is, what this new thing is about? All right. So typically, antiderivatives, if lowercase f is a function, then capital F, these are the capital of the same letter, is used to find its antiderivative. So we call some function capital F an antiderivative of f on some interval if this is true. F prime of x equals f of x. So if I say capital F is an antiderivative of f, that's the same thing. That's the derivative of capital F. On that. Yeah. And I think we've talked about this idea in the past, but oh no, this is something I'm thinking a bullet ahead. So if capital F is an antiderivative of f, then the most general antiderivative of f is what? And this is essentially what you all just said, or not what a few of you said. If I have some function f and the antiderivative exists, what is that antiderivative? As we said, it's not enough to say it's f of x, right? Or capital F of x. Yeah. Because really they could differ by any constant. And one last question for you. If I have some function f, lowercase f, such that capital F prime of x and capital G prime of x are both f, how does that end in f and g? Are they equal? Let me ask it this way. Could capital F and capital G be equal? Something like a seconding of that. So to kind of give you another hint here, someone throw a function at me. That's enough. Yeah, we want to keep it simple. So I have a capital or lowercase f of x is equal to 6x. I'm going to say this. I'm going to say, okay, I get to choose capital F of X. I'm going to say it's 3x squared. If you're allowed to choose capital G, do you have to choose the same thing I did? So because of that, how are F and G related? It could be different, but they're going to be different by a constant. I say capital F of X. Are we okay with this idea here? All right, moving on. Let's find the most general antiderivatives for each of these. So I have f of x equals sine of x. I want capital F. Negative cosine x, incorrect. There you go. So in this case, I'm asking for, yeah, give me the catch-all. Give me the most general version of this that you can. Negative cosine x is an antiderivative. It doesn't really capture all the possible things. All right, g of x equals 1 over x. Oh, no one tried to, did anyone fall into the product rule trap? How does product rule work on that one? X to the 0 over 0. Just everything falls apart, right? So hopefully we're okay with this idea, the natural log of, and for now, I'm going to ask you all to take this on faith. Natural log of the absolute value of x. Talk about that. Actually, I'll start off with that on Friday, but we've actually kind of talked about that idea before, but if you had no idea that antiderivatives were going to be a thing in your life, we had no reason to talk about it really. All right, and then h of x, I'm basically asking you for the product rule, right? So if I give you some function where x to the power of n, where n is any real number that's not -1, what do you do? Over. Is that what you said? Yeah. Incorrect. There you go. And one thing I want to highlight means the fact that these anti-differentiation and differentiation are inverse to each other. Think about the way the product of the power works here. You multiply by n, and then you you invert between those two steps in the opposite order and do the opposite steps. So I'll give more detail on that on Friday. 1 over x it involves that absolute value. All right. I'll